Yeah, all right, so this is the second in the series on JAX, and here we're going to go into the depths of JAX for optimization, but first we've got to motivate it. And so, yeah, I'll just start by motivating satisfiability and combinatorial optimization broadly. So yeah, next slide. Takes a while to update. There we go. Yep. So satisfiability, it's a Boolean optimization problem. And before I get into the depths, I'll sort of give, whet your appetite for why you might want to get interested in this. So very recently, in fact, this is pre-press, one of the folks that was still on the project, a bunch of people from the CSIRO Health and Biosecurity team have been using satisfiability and optimization and satisfiability to create synthetic genomes. So that's this Genominator project. And by using SAT, they have a logical approach to synthesizing these genomes. And that has a couple of advantages. One of them is that you can be a lot faster, so orders of magnitude, thousands of times faster than incumbent methods, such as using kind of machine learning models, GANs and things like that. And the other advantage of using a logic SAT-based approach is you can actually be provably privacy preserving. And so you can make sure that you can't identify individuals that are in the corpus from which you're making synthetic genomes. Further to that, with the logical approach, one of the advantages that they're spruiking with satisfiability, and this is useful in the context of the American College of Medical Genetics, say that significant findings, whether they're in synthetic or otherwise, need to be, if they're relevant to someone whose genome appears in the study, then that person ought to be notified that there has been a significant finding. And if you have this logic-based approach, you can recover the individuals from which a synthetic genome was synthesized, and therefore you can notify them when there is a significant finding. You're still privacy preserving because you need to be the data custodian to be able to recover that. So that's one example, synthetic genomes of satisfiability. Another example from about 10 years ago, so in 2009, North American broadcasters, TV broadcasters in particular, started using digital TV. When you use digital TV, you can repack broadcasters into channels. Sort of the channel is about 6 megahertz of range. So following that, in 2012, the United States government passed the Spectrum Act, and that essentially enabled them to run this reverse auction, an incentive two-sided auction, to reallocate the 600 megahertz spectrum to high economic value activity like wireless internet away from low economic activity broadcast television. And so they ran a reverse auction, and during this reverse auction, they needed to repack TV stations that weren't selling spectrum for use in wireless comms into sort of, let's say, the 500 megahertz band from the 600 megahertz band. So they would repack them into other channels, and that repacking problem was solved by satisfiability. And to give you a sense of the scale of that, it's an optimization problem with about 70,000 odd Boolean variables. The number of constraints was in the order of 3 million, as they reported, and they were solving about 100,000 of these problems to run the auction to see whether or not what they were proposing was actually viable, satisfiable, whether TV stations could still continue to broadcast if they weren't selling their spectrum. And they were running that on a fairly small host, so they were running it on a 8-core CPU host here. And so, again, motivating satisfiability. So now that I've motivated it, hopefully got people a little bit excited about it, I'll actually define it. And so let's just see what a satisfiability problem actually is. So you've got propositions. These are Boolean variables that can be true and false. So the fact that I'm talking now is a proposition. And then from you start to generate expressions with the usual operators for Boolean circuits. And so you can generate an expression here, x and y. So the expression x is true and the expression y is true. You can do disjunction, so x or y. We've got material implication. So if the expression x is true, then the expression y also has to be true. And then we have negation. So we've got the ability to talk about if a proposition is true or if a proposition is false. So those are the building blocks we have to build expressions. And from there, we can talk about Boolean satisfiability problem. So the problem is to find an assignment, so truth valuation to those propositions that satisfies an expression. And so to do this, we want a canonical format in which to express things that's amenable to algorithmics. And so that canonical format is this DIMAX conjunctive normal form format. And to describe that, We talk about propositions and their negations as being literals. So from literals, we can talk about disjunctions over literals. So here I got P1 or not P3. And from there, I can take the conjunction of those disjunctive clauses to make a problem. And so any formula in Boolean logic can be represented in this way. And there on the bottom left corner, I have an example of what an input file actually looks like when you're using a SAT solver in earnest. So you have a problem. It's a CNF represented problem. You've got three variables and 2 clauses. And then, line by line, you kind of enumerate those things. So let's do something useful with this. So Sudoku, hopefully people are familiar with this. It's a good way of spending time when you need to spend time and don't have something economically useful to do. So you have Boolean variables that say whether a particular digit V is in a particular row and column ij. And so those are the Boolean variables in our problem. And then the Sudoku constraints that hopefully everyone's familiar with is that a number in a cell in this grid, so it's a 9 by 9 grid, a number can only one number can be in a cell, so an exclusive thing. So you say, well, for every cell I and j, and for every 2 digits v prime and v that are the same, either v, v is in the cell, then v prime is not in the cell, vice versa. So you have a disjunctive clause for that. You can also talk about the fact that you have to complete the Sudoku puzzle. So every cell in your Sudoku puzzle actually has to have a digit in it. That's the next one here. And then next slide, we talk about every row needing, every digit has to be represented in every row, which is the first constraint here. Every digit has to be represented in every column, which is the second constraint here. And then every 3 by 3 subgrid needs to have every digit. So basically, you can succinctly represent the Sudoku puzzle with a bunch of clauses in CNF, which is kind of what we're trying to communicate here. Yep, so next slide. So this is an NP-complete problem. It's a canonical NP-complete problem. I think the first to be shown, and it sort of describes NP-completeness. Algorithms to solve SAT problems are exponential in the worst case, which is no fun. And here are some of the algorithms. So philosophers have talked about, and computer scientists have talked about how to characterize, optimal decision procedures for the satisfiability problem. Those are resolution. Those are syntactically described procedures. Today, we're really interested in stochastic local search. And so characterizing the satisfiability problem as an optimization problem and doing search to solve that as an optimization problem. And then sort of the incumbent best systematic procedures that are complete are these procedures called DPLL and CDCL. These are backtracking search procedures. So how do you be systematic about this when you're given a problem? So I just want to give a flavor of being systematic. So this is this conflict-directed clause learning procedure. This essentially characterizes the state-of-the-art in sound and complete procedures for solving the satisfiability problem. And essentially what this does, if you glance at the pseudocode, is it comes up with a bunch of decisions D, and it grows those sequentially. And when it finds decisions which conflict with the constraints of the problem, it posts a new constraint, which is the reason for that conflict, and then revisits that list to deconflict and pursues that. So essentially, that's how a systematic procedure works. And of course, you can add a lot of bells and whistles to that. But what we're interested in today is in treating the satisfiability decision problem as an optimization problem. So here, we're going to be incomplete. We're just trying to find a satisfying valuation. And the way to do that is to, given a complete valuation, characterize whether a clause is or isn't satisfied numerically with this function f. So f takes a complete valuation and a clause. It gives you a 0 if the clause is satisfied, a 1 if the clause is unsatisfied by that valuation. And then the value of an assignment with respect to the whole problem is just the number of unsatisfied clauses. And then once you've done that, you can treat it as an optimization problem. So minimize the number of unsatisfied clauses with respect, find an assignment which minimizes the number of unsatisfied clauses. How might we do this in practice? Well, you just start at some arbitrary position in the space. So just Boolean vector, giving an assignment to all the propositions in your problem. And then you can just flip them one at a time, greedily, for example, until you find that you've satisfied all the clauses, or perhaps, until the death of the universe or something like that, right? And so you can do some restarting. And there's a whole menagerie of different local search procedures to solve this. An algorithm that you can play with, which allows you to do this in HPC environments and allows you to mix that systematic search with the local search I just described, is this JAX tool. So I just want to give a shout out to that now. That's what a lot of the development we're doing is kind of aimed to be against. And there's some tutorials, a link to some tutorials there that you can grab to start playing with that SAT procedure if you wish. But now, I suppose, on to continuous local search and solving this with JAX optimization libraries.
Hopefully everyone can hear me as we swap the microphones over. Great. Okay, so continuous SAT. As Charles has pointed out, we are interested in how to treat SAT as an optimization problem. And those familiar with SAT and those who have just digested all of Charles's intro might think, well, we have quite good approaches for state-of-the-art SAT solving that have been developed, for decades now, half a century even, that are NP complete. But when we take this as an optimization problem, we're essentially moving into a harder space of undecidability. So why would we bother with this to begin with? Well, the first is that we have a new generation of high compute devices. And notably, in terms of libraries, and today we're talking about JAX, existing approaches for SAT don't really leverage GPUs or TPUs. If your cloud is composed of entirely CPU-based devices, then I suppose you could theoretically deploy DAGs to it as an example. And we also have auto differentiation, which is not exactly novel, but it has vastly improved our ability to train these sort of massively scaled sort of neural networks and LLMs. That in our compute is increasingly distributed and, as I said, heterogeneous. So we now have not just CPUs to play with. Parallel SAT, as we've pointed out, is mostly built around many CPUs with bit flipping and clause satisfaction checking. These operations aren't really well suited to GPUs or TPUs necessarily. Ideally, we want nice matrices and matrix products and vectorizable operations. And are we leaving opportunities on the table? Sort of this apocryphal example is that neural networks were sort of resurrected from the grave 40 years later, and with the benefit of more memory and modern compute, have now spawned this sort of LLM boom that we're in the midst of. Whereas back in the 50s and 60s, they were just seen as a bit of a toy that couldn't do much. So okay, that all sounds great. How do we actually do this? We need to convert our SAT problem into some sort of continuous form. We want to take this from a binary decision or a Boolean decision problem into a continuous space that we can optimize over. This is in the literature referred to variously as the Walsh transform, or the Walsh Fourier transform, or the Walsh Hadamard Fourier, or the Walsh Hadamard Rademacher Fourier transform variously. But importantly, and what's important here is that this is not a new technique. Sort of this transform was introduced by Walsh over a century ago. So essentially what this means is we can take any expression, any SAT problem, in Boolean variables and transform it into a multilinear polynomial. You'll see here the definition on the screen, this FE, the Fourier expansion of F, over your assignment vector is this sum of all possible subsets of your variables. That's the 2 to the x, it's power set notation for those who haven't seen it, multiplied by this F hat times the product of all the variables in that subset. So F hat we call the Fourier coefficient of F at the subset that you're currently looking at of the variables, and it's computed separately. Now, quick example here, we have a very simple logical expression that could be part of a SAT problem, x1 or not x2, and not x1 exclusive or x2. The Fourier transform here is that equation on the right, and this is just a generic polynomial that we can perform minimization over. So some quirks and properties of this transform. We're used to mapping true and false to 1 and 0 respectively. As we just saw in Charles's example in the discrete case, when we convert to an optimization problem, we take true as 0, so we can minimize the number of over the number of true clauses. But this is sort of against intuition. And in this setting, we actually take -1 as the default for true. What's nice here, though, is that the Fourier expansion of the formula into the continuous relaxation approaches this true value, -1, when x approaches a satisfying assignment. Two more nice properties. When our current assignment vector is within the -1 to 1 cube in all variables, so this is a hypercube in n dimensions, the actual evaluation of the Fourier expansion also stays within that box, which is the box we care about. Notably, this is a continuous relaxation, and so it extends to the whole plane of R. Outside of the bounds of -1 and 1, the expression is somewhat meaningless for our purposes. And the last sort of nice property here is that if our assignment vector x is all exactly -1 or 1, then the Fourier expansion will also be exactly -1 or 1. So the construction of the expansion, is quite nice for us in this sense. But as I've said, this already looks quite bad complexity-wise, right? We are taking the sum of all power sets of our number of variables. That's 2 to the n terms. And the number of terms we have can also be quite large, even for moderate problems. I think the two examples that Carl's mentioned, especially the auction of the radio frequency spectrum, that was millions of clauses in how many variables? 70,000, right? So 2 to the 70,000 is already outside of the range of sort of any sort of modern hardware to compute optimally and check every combination. That and computing f hat, or these Fourier constraints, for some arbitrary Boolean expression is actually, in general, harder complexity-wise than SAT itself. So this all seems not great. However, there is a reason. So I'm briefly going to detour into what we call symmetric pseudo-Boolean clauses. So when we're talking about SAT problems, a pseudo-Boolean clause in general is actually the summation of each of our variables times some constant weight compared to some other value k. We'll go back to the classical treatment of true and false here as 1 and 0. And the expression here, 5x1 plus 3x2 minus x3 is greater than 4, is an example of a pseudo-Boolean clause. This can be converted into CNF. The conversion is not necessarily nice or pretty, but it can be. And in this particular case, one example satisfying assignment would be x1 is true, while x2 and x3 are false. And if you play around with that, you'll find other assignments will be greater than or less than 4. So a symmetric pseudo-Boolean clause are those that only rely on the number of true variables. So in this case, all of the constants or the weights are 1. All we care about is the count of the true variables. And it turns out these symmetric clauses are actually the ones we care about. Most SAT problems, or most Boolean logic problems, are composed of these symmetric constraints. And nicely for us, the Fourier constants, which I said were in general harder to compute than SAT is as a problem, we actually have closed form solutions for that run in, at worst case, sort of n log time. So these sort of 6 clause types are the ones we see the most often. So at most 1, exactly 1, these sort of names are self-descriptive, not all equal, so at least one of the variables must be different from the rest. They can't all be true or all be false. Exclusive OR is the operation we're classically familiar with. And when you are taking the exclusive OR of more than 2 variables, really what you care about is that an odd number of them are true. If you take sequential XORs, you'll find that this is how it works. And then for cardinality, we just care that some number of the variables in the clause are satisfied or unsatisfied. So this can be less than k or greater than k. variously. Now, why this matters is if we were to take a problem that would natively be expressed with these pseudo-Boolean clauses, like this would be the most natural way to express the constraints you're dealing with. To use classical SAT solvers, you would need to essentially ground those clauses in CNF. And it turns out for some of these, the actual CNF representation of a single clause requires many, many more CNF clauses to represent. Notably, cardinality naively, is n factorial in terms of representation. There are much better representations, but there's usually additional compute overhead as well to compute these representations. So the reason why we care here is that we can actually keep these pseudo-Boolean clause types in their native form, or at least as a one-to-one map in our continuous relaxation, rather than blowing up into possibly, n squared additional clauses. When n is large, any sort of quadratic or worse is not great for us. An important point about cardinality itself is that of all of the different CNF reductions, it's typically unclear as to which one will be the best for any given setting. There's a whole separate body of literature for cardinality in itself of people exploring different CNF conversions, different ways of representing cardinality that are tailored to different domains that perform better or worse across the board. And some of them involve their own substantial compute to even, perform that reduction. And importantly, all of these also show up in real problems that we care about. Notably, ZORs are all over the place in crypto. In terms of routing problems, classical traveling salesman, or from those who are, familiar with other sort of decision problems, diagnostics, planning. There are you would natively want to use these clause types in these settings. And a point to Sudoku, Charles's representation in CNF is the classical CNF representation, but it can actually be represented with many fewer clauses using exactly one natively. So you could take all of the positions for a 9 in one row and say exactly one of these is satisfied, right? And so you end up with fewer clauses overall. So we have this ability to convert our Boolean expressions into polynomials, multilinear polynomials. Here's 2 examples. I should say both of these images are taken from this work, Parallelism et al. That was also referenced on a previous slide, as well as a foundational textbook on the analysis of Boolean functions. A lot of this work builds off this Parallelism approach. This is actually Moshe group at Rice University, for those who are familiar, sort of one of the titans in SAT and logic. And so there's a few references here. I'm borrowing some images from their paper. On the left, we see this simple expression x1 and x2. Now, keeping in mind that our treatment here treats true as -1, when we plot this function in 3 dimensions, we can see that indeed, only when both x1 and x2 are -1 does the actual topology of the function itself reach -1. For all other situations, especially when one or both of the variables are false, we end up with exactly 1, which is false in this treatment. On the right, we have the example from before, this x1 or not x2 and not x1 XOR x2. This is slightly more complicated. We can see we have a saddle point, which those who have done gradient descent approaches or optimization approaches are already a bit scared. Saddle points are generally not great for us. But also we can see here that this graph extends out to 2 and -2 on the z-axis, just to indicate that, yes, this function does extend outside of our bounding box and is still smooth and continuous the whole time. But notably here, we can see that our 2 satisfying assignments are x1 is false or x2 is true in the 2 opposite corners. And those are the evaluations to sort of -1, or that will cross the line at -1. Okay, so I've already said that computing the Fourier constraints is more difficult than SAT, but we have these nice close forms for the clauses we care about. And that's important because most SAT problems are actually composed of separate clauses. If we were to combine all these clauses into one massive expression, looking at this previous slide, the example on the right is technically two separate clauses, but you can treat it as one full expression. That is difficult to take the relaxation of. It is quite a hard computational problem. However, if we can decompose our problem into a list of symmetric clauses, each of those have, as I said, at worst, n log n sort of complexity to compute the Fourier constraints over. So this is looking a lot better, right? So instead of taking the Fourier expansion of the equation originally, we take the Fourier expansion of all of its individual clauses. Now, in this particular case, this formulation of the Fourier expansion of f isn't exactly, but it does serve as a surrogate or proxy in that it goes to -1 in the same places that the true relaxation would go to -1. It also goes to 1 in the same places that the true relaxation would go to 1. Because normally that equation would evaluate to -1 or 1, but because now we're taking the sum of m clauses, technically our bounding range for viability is between -m and +m, right? If all the clauses are false, then each one evaluates to 1. There's m of them, hence the evaluation of our surrogate representation would be m. Having said that, we have a nonlinear bounded optimization problem, which is sort of exactly what we were going for. And that is we want to minimize our Fourier relaxation over our assignments, subject to the assignments being in our sort of viable, feasible box. And notably, if that expression ever evaluates to -m or thereabouts, we can essentially say we have a satisfying assignment. Now, a brief note on completeness here and to the binary setting as well in the optimization problem. These methods are incomplete. They can't prove unsat. To do that, you would have to explore every possible assignment. There's 2 to the n of them. So they aren't complete. There are sort of some ways around that, which we might talk about towards the end, but you essentially need global optimization, which over a non-convex, non-linear objective function is quite difficult. Great. Okay, so now we get to the JAX part, which I think is what some people here are mostly interested in. So why JAX? A couple of factors. For those who were paying attention to the relaxation before, we were taking the product of all possible assignments in the subset related to that clause. If you've ever heard of the elementary symmetric polynomials, that's exactly what that is. And it turns out that taking the sum of all possible elementary symmetric polynomials in n variables is in itself quadratic at the worst, but it's vectorizable if we use some Fourier transform tricks. So this is Fourier on top of Fourier, but notably the convolution theorem through Fourier space means we can perform this highly vectorized, and essentially I think it becomes sort of log n at the worst case if we can ideally parallelize the problem. All of our minimization algorithms over smooth continuous functions want to make use of first and second derivatives. Normally we would have to compute these explicitly, but in this particular case, JAX has auto differentiation, so that removes the need for us to compute manual gradients. So we can see that JAX sort of has all the tools we need to compute this problem. And importantly, we also have just-in-time compilation with JAX to compile very, very fast GPU kernels. And for those who were here last week, we saw that sort of JAX has managed to achieve near perfect scaling with with additional resources, additional GPUs, TPUs, etc. I won't talk explicitly about sharding today, but it's one of the tricks that you can get. If you have more GPUs available to you, you can get more throughput. So some observations here. there are still 2 to the n possible assignments. So a gradient descent with a single starting point is not going to cut the mustard here. We'd have to be very lucky. It would have to be in exactly the right part of the space that finds the global minima, if the global minima even exists. And in our observations, toying around with this problem, anecdotally, there are many, many saddles and also many local minima to negotiate. It's just sort of the character of the topology, which is also not great for a lot of these minimization algorithms, especially those that are in the first order. Sort of Newton methods can use second order derivatives to avoid saddles, and there's a lot of work recently in the literature about saddle-free optimization. But typically they don't operate in the bounded case and make some other assumptions. But in any case, we want as many simultaneous gradient descents as possible, so that hopefully one of them finds a satisfying assignment. Which also, as I just mentioned, JAX is highly vectorizable, so we think we can do this. Hopefully this is readable. I'm just going to now talk through the JAX pipeline for the SAT problem, or at least this continuous relaxation, and a few improvements that we sort of made, which should be applicable to other people working with sort of continuous relaxations of these types of discrete problems, where you're trying to maximize the number of points that you're testing. So we define our evaluation function and our validation function to check that, well, firstly, we have to compute the valuation. I won't go through the Fourier mathematics today, but it's in sort of the papers that have been referenced. And then the validation just checks that with the current assignment, whether the clause is true or false. We then define our optimization routine. Notably, we set up our solver, we set up our optimization function, and you'll note that there is a at jax.jit directive annotating that function, which is a declaration that we want this to be compiled as a fast GPU kernel. And the last line here, we have this jax.vmap or vector map. So for our input batch of x points, we are going to map the optimizer over those x points. So single instruction, multiple data. And JAX is very good at this. It essentially adds a batch dimension to all of your inputs and outputs and optimizes as much as it can the compute sort of tree. And hopefully, if people come to future JAX presentations, they'll get some more detail on how this actually works. So once we've done all of that, we then need to actually proceed to attempting to find a satisfying solution. So we generate a batch of random starting points in our space between -1 and 1. And we call our compiled optimization routine. And in this snippet of code, this will continue to loop forever until it finds a satisfying solution. You can add a timeout, probably sensible, because we still haven't escaped the bounds of exponential complexity here. So this could still run until the heat death of the universe, if it's unlucky. And notably, I'll start talking about how these improvements and how these changes sort of affect our problem going forward. So with this particular version on a given target problem that I will use as reference, we get sort of 3,000 simultaneous descents before we cap out our memory on a single GPU. So a couple of improvements we can make. This one I think will be relevant to a lot of people working in these discrete decision problem spaces, where our objectives might not necessarily be naturally expressible as a single matrix or as a single array. In that treatment we were just looking at, we were treating that as a single array. Now, it's important to note here that there's a reason for this in JAX. When you are compiling a function, JAX will trace at runtime the input shapes for that function and optimize it, expecting those shapes, those exact sizes, to be present every subsequent invocation. So I can't decompose my matrix into smaller arrays and have multiple smaller arrays calling the same function. It will sort of panic and say, this was compiled for a different shape. But to achieve that, we had to treat it as a single array and introduce a lot of padding so that we could treat it as a single objective. that we were vectorizing our evaluation over. Here, we want to save on that memory. So in this case, instead of a single objective with the Fourier transform terms and the mask, which was keeping track of which cells were padded and which weren't, we instead have this separate clauses routine where we break it down by size. So now we have possibly collection of sub-objectives that have no padding, but are confined to like clauses of an equal size, or all the length 3 clauses or the length 4 clauses, etc. And that's in the number of variables. Now, I just said that the compiled function doesn't like this, right? And so to get around that, we introduce an additional function sort of over the top of our original routine that just sort of loops over the objectives and computes it separately. Now, JAX sees the loop. It understands that there will be multiple objectives coming. And so it eventually ends up compiling a separate version of the evaluation function for each of our inputs. The problem here is that in the loop here is expressed in Python, and by default, the treatment of that in JAX is it has to call back to Python, which is notably slower than sort of compiled code. Having said that, this one optimization gets us almost 5 times the number of points, right? The amount of memory we save, not padding, means we can push that much more throughput. But due to the loop being handled at the Python level, we lose some compute performance. But we can actually group more aggressively as well for more memory savings. If you grouped by both clause type and clause length, you get some additional gain in terms of the Fourier transform tricks that I was talking about. If you are using combined matrices or combined arrays, you have to express the Fourier transforms individually for each clause. But these transforms only depend on the clause length and the clause type. So if you group by both, you end up only needing to have one row, for example, rather than an array of rows. And so there's ways we can get around this memory optimization, this memory cap, rather. Okay, so that's great. It'd be great if we could get around this loop problem. So we just had this iteration over the objectives, over each of our sort of groupings of equal length. Turns out we don't have to loop at all if we're a little bit clever about it. Now, this is a function with a bunch of subfunctions or sort of member functions that build a combined evaluation. For those who haven't seen closures before, we refer to this as a closure. So here we provide this build eval function with just our list of objectives. And it sort of will build some functions that have local scope and local visibility over each objective, sort of built in as constants, right? Essentially, we're saying construct a function for each objective where the objective is a constant already saved in sort of the data for this function. So we loop over each of them and run this single eval closure, which is the function above, which essentially is exactly our evaluation from before, but it has sort of the subparts expressed as local variables. We then build a function that essentially vmaps over each of these and evaluates them together. You could do this theoretically as a loop as well if you wanted to. It would be faster up front because JAX already can see that there are a bunch of incoming functions. Now, the reason we care about this is because at runtime, we don't necessarily know how many objectives we will have. But once we've processed our incoming problem, we know exactly how many types we have. The problem is we can't define an evaluation function that arbitrarily works for a single function that for n possible inputs. So this allows us to be flexible and still give JAX all the information it needs to compile all the necessary shapes and GPU kernels sort of at runtime. So same number of points still in this particular case, but we definitely have some speed regained because we no longer have this explicit loop in Python that JAX has to call back to check at each step. And I suspect this particular improvement might be relevant to a lot of people who are maybe working with these types of relaxations, a lot of these decision problems in planning or diagnostics or frequency auctions will have varying lengths where we ideally don't want the memory overhead to treat them all as a single unified objective. So lastly, and I think this one is also quite important, checkpoints. And no, not the kind that we're used to in machine learning, where we are saving the model state to disk. In this particular case, a checkpoint for JAX, at least in this treatment, it means both, is a flag to the compiler that for the function that it is annotated with, this JAX.checkpoint, we can discard the intermediate terms. Why this matters is because when we are computing the forward pass, JAX will normally keep all of our intermediate products, all of our intermediate expressions, such that when we go to perform order differentiation later on, and we do the backward pass, it's also quick to compute. Now, this will be a trade-off that individual problems may or may not benefit from. In our particular case, our largest intermediate product, this sort of prod term, is by far the largest in the evaluation sequence of operations. However, it's very fast to compute. It is simply a vectorized addition and then a product of those terms down an individual row or column. This is not a complex operation for a GPU to perform, so it's very fast. So in our particular case, we tell JAX explicitly that on the forward pass, it can forget about this and recompute it on the fly. So in this case, we're explicitly saying, I want to trade off future compute for more memory now. And in that case, and for this target problem, we get almost double the throughput here. By telling it can ignore this intermediate step, or it can discard it as soon as it's computed it, it's much better able to optimize the memory allocation. Now, JAX will do this sort of by default. If you run your own code, you'll occasionally see that it will throw memory errors or memory warnings and say that it could only materialize down to a certain size. What materialize means here is to essentially resummon a matrix it had previously discarded. The checkpoint here says, save the clause assignment so that we can recompute this later when we need to. The JAX developers, sort of explicitly in the documentation, do say that you are likely to get better performance doing this yourself rather than relying on JAX to do it for you. JAX, I think, will be aggressive in trying to hold as much in memory as it can, and it will throw away, I think, the smallest intermediates first, assuming that the smallest are quicker to compute. In our case, I explicitly want to throw away the bigger ones because they are very fast to evaluate. And my clear takeaway here is manual memory management is still a thing in 2025. Alas, for us, it's a massive benefit. But if your large intermediate products also have high compute associated with them, this may not be necessarily an optimization you want to perform. And there are more improvements we could talk about here. Notably, I sort of skipped over sharding. For a problem of this nature, these matrices, I guess, are quite small with respect to the number of points we wish to push through. Like, we would like our memory to be dominated by the number of sort of starting points we're picking in our gradient descent. But that, sorry, I lost my train of thought then. Sharding, right. So if we have multiple GPUs available, we can just say, duplicate all of our objectives, which are fixed at runtime, to every GPU, and then just give a completely separate batch of starting points to other GPUs. Hopefully in a future JAX presentation, we get to see a more explicit example of sharding. You can define like a 2D grid, and you can say, I want to distribute one of my matrices over like the horizontal axis of the grid, and I want to distribute the other product vertically. So if we had a very large SAT problem where our objectives were actually a limiting factor on memory as well, we could sort of break up each objective onto a separate row of our grid of GPUs and then push the same batch of starting points across each row, where each vertical slice then represents a different batch of starting points. So there's some very cool things you can do there. And again, the overhead is very minimal. You get near linear scaling, near ideal. So to conclude, whether this is an appropriate treatment for SAT is still to be determined. The work being done by Moshi's lab at Rice and by us shows some promise for some of these pseudo-Boolean clause types, notably cardinality. We get some quite good results on some synthetic benchmarks. We have yet to replicate these in practice, but if we can integrate these with existing tools like JAXter, we might be able to have some breakthroughs in terms of solving these types of problems without the overhead of converting these pseudo-Boolean clause types into native CNF. That's a non-trivial problem. We would have to decide when and where we pass partial solutions, or when and where we expect to evaluate pseudo-Boolean, or where we expect to convert to CNF. There is a lot of heuristic optimization. If you go look at the SAT competitions and how different solvers work, they will attempt to study meta parameters of the problems to determine optimal solutions. Portfolio solvers are also common. There's the 10 most performant SAT solvers all do 10 different things. So one way to do things on CPU is you just launch all 10 of them on your problem and see which one returns first. But we can also get performance gains by having them talk to each other and share what they've learned so far. We also have very fast evaluation of our objective in this treatment. So there are other approaches that aren't explicit gradient descent, like annealing or multi-color methods, Moreau envelopes that also might be worthwhile exploring here as an additional tool. But I think that wraps it up for us. So I think we have sort of just under 10 minutes left for questions, if there are any.
I have a question.
Yes.
So whilst you say it's, you're still determining whether this really works in the wild, what's the step to sort of productionize this and then use it in those applied use cases that Charles spoke about at the start? Do you just release a library and hope that people use that, or what's the best way to do it?
Yeah, so I guess there's two things here. We can just release the current Python code as a library. It does work. Whether it finds a solution for your problem, big question marks. But again, SAT is classically an NP-complete problem, and we aren't going to escape that by relaxing into what is technically a harder problem. Our next step is to actually do some integration with JAXter as well. Now, JAXter is written natively in C++. Now, whether we want to integrate Python code as a sort of a pipeline to production release, for example, is up in the air. What's nice about JAX is that the underlying compiler, XLA, also another product from Google, you can tell it to save the compiled code to disk. So we could actually have a cache of compiled functions that are sort of just binary blobs that could be called from the native C++ without going through the Python overhead. Alternatively, we could just re-implement the whole thing in native C++. We lose sort of the benefit of some of the clever things that JAX does, but auto diff is available in C++. I mean, all of the fundamental parts of this are actually implemented, under the hood in C++ fundamentally. So that's one option. We could just leave it in Python with JAXter and just have it compile through Python on the fly, like it works in Python. We trust sort of the JIT compilation chain through XLA to give us, well-optimized code for our infrastructure. So that's also an option here.
Cool.
In terms of wrapping this up into a commercial product, I mean, DAX, they're both very much academic tools. I think they would need, quite a bit of engineering work to make them maybe sellable. I'm not sure. Need a marketing department, says Charles. So
I have another question, but is there questions from anyone else? All right. So I'll ask my other question. In like 10 years time, when GPUs are cheaper and faster, are you still going to use the same approaches, same methods, or is there like a better strategy? This seems to sort of scale well as GPUs get bigger. So,
I mean, that's a good question. There's sort of this idea of we can't really predict the future in terms of what other novel ideas people might come up with. But as far as utilizing GPUs, this is probably our best option right now. There's a couple of, yeah, go ahead. Yep.
So, I mean, I can have an answer to that. One of the things we do when we're solving, well, essentially we want to scale either to bigger problems or we want to scale to problems that are more difficult. In either case, you want to, if you have a lot of infrastructure which is distributed, you want to be able to exploit the compositionality of that. So at the moment, the tool that we're developing against, this DAGster C++ incumbent code base, has schemes where if you know the compositional structure of your problem, you can then exploit that to take advantage of multi-CPU cores. And we'd expect to do the same with GPU cores. And so, if a single GPU is bigger, that's great. We can post bigger subproblems to that and get, speed up without network latency. And then if you have lots of GPUs, well, if you have a problem with compositional structure or where there's a lot of subproblems that need to be solved and you can solve them independently in parallel, then you can take advantage of that. So essentially taking the same recipes that we already use and just using those in heterogeneous environments, compute environments. The other thing I would say is that there are and then the question is, okay, where do you get your compositional structure from? So, our group has some planning papers that look at discovery and exploitation of compositional structures. Most recently, Ava Clifton's been publishing in that space. And so there are recipes in the literature for doing this. And so it's not like no one's thought about this. If you go back to the late 90s, early this century, you see people characterizing the hardness of these combinatorial problems in terms of compositional structures and treaty compositional structures of the constraint problem. And so that's kind of the starting point for that.
Fantastic. All right.
But as GPUs get bigger, we can always, because our problems are exponential, we can the problems, we can always come up with another problem that will be too large for whatever infrastructure we have.
Well, that's what I was thinking. Like 20 years ago, this would have been super hard to do, I guess.
I mean, certainly this wasn't a concept, like as I think I pointed out, the transform has been known about for nigh on 100 years.
Yeah.
It's mostly just been something that mathematicians care about. So we're doing something like reinforcement learning. How would this approach work? How can I use it to improve memory use for reinforcement learning?
And the reinforcement learning question could be something about sort of the DQN workflows, what you would use to do, network-based agent optimization with JAX. I don't think we can comment on that.
No, I mean, so I guess fundamentally JAX and a lot of the infrastructure around it is being built as a sort of machine learning forward library. So I think if you are just defining your networks as you would, say, in PyTorch or TensorFlow, you can re-express them in JAX natively and benefit from all of the advantages that JAX provides. In terms of improving memory usage, I think in that particular case, your matrices are already dense. The one thing I might think about there is if you have sparse intermediate products, you might look into matrix decompositions, right? Matrix factorizations in some of your intermediate layers. If you happen to know that they are sparse. JAX does have some experimental support for sparse matrices, but it is clearly experimental at this, and I'm not sure what the development stat of that is. But that would be where I would look. If you're trying to explicitly save on memory, look at where you're doing unnecessary padding, or where you can better represent sparse intermediates as sort of dense intermediates. Or just, throw away intermediates with checkpoints and just, if they're fast to compute, let JAX recompute them on the backward pass. This would mean you could conversely scale the number of sort of the depth or the height of the layer. If you know you're just going to throw away that intermediate product as soon as it's done, JAX can then optimize around that. But again, unless it's cheap to recompute, you might want to experiment and play around with that, whether the trade-off is worth it to you.
All right. Yeah, thanks so much again, guys, Cody and Charles. I'll get the recording up as soon as possible, but thanks everyone for coming, and thanks for presenting. See you all again soon.
Thank you.
Thanks for organizing. Bye.